we have covered topics like elliptical lift distribution, aspect ratio, and problems related to elliptical lift distribution and then aspect ratio. Now, in this session, we will be covering topics regarding compressible flows, and in compressible flow, what is a shock wave, and what are the different types of shocks, and what is a normal shock. So first of all, before entering into the topic, we should know what is a compressible flow. So we all know what is a so what is compressible flow. The compressible flows are high-speed flows. In this, the fluid density varies with pressure. That is, density is not equal to constant. But we all know about incompressible flows. That is, incompressible flows are flows in which the fluid density is constant. So throughout the flow, if the fluid density is constant, means it is called incompressible flow. And throughout the flow, if the density varies, means it is called compressible flow. So therefore, rho not equal to constant for compressible flows. And based upon the Mach number, the flows are classified as incompressible flows. That is, incompressible means Mach number less than 0.3, and compressible flow after beyond 0.3, everything is compressible flows. And in that also, based upon Mach number, the flows are classified as if so m less than 0.3 is incompressible flow, then m less than 1 is subsonic flow, then m equal to 1 is sonic flow, then m greater than 1 is supersonic flow, then m greater than 5 is hypersonic flows, and another one is the transonic flows, that is between 0.8 to 1.2. So this is how the flows are classified based on the Mach number. Then for compressibility, there is an important term called for compressible flows. There is an important term called compressibility. The compressibility is defined as the amount by which a substance can be compressed is given by a specific property of substance. So it is also defined as the change in volume of fluid element per unit change in pressure. So change in volume of the fluid. So fluid volume, there is a change in volume per unit change in pressure. So the formula is tau equal to minus 1 by V dou V by dou P. There is a change in volume divided by change in pressure. So for isothermal process, the formula becomes tau suffix T equal to minus 1 by V dou V by dou P of T. For isentropic process, the formula is tau suffix S equal to minus 1 by V dou V by dou P of S. If we are considering for density means, then we know V equal to 1 by rho. Therefore, tau equal to 1 by rho d rho divided by dP. So here is in this diagram, you can see that so first of all, the pressure is applied to a particular volume V. This is the volume, and while applying some pressure, the change in pressure will be P plus dP, but the change in volume is there is a change in volume also. That is represented in the second figure. That change in volume is, we will represent that it as V plus dV. So all the whole, the compressibility is the fractional change in volume. That is the del V divided by change in pressure through over the particular volume. Then the degree of compressibility is categorized by bulk modulus of elasticity, or else it also classified as a volume modulus of elasticity. So the bulk modulus K equal to bulk stress by bulk strain. By substituting the formula, we will be getting K equal to 1 by tau. This is not T, this is tau. 1 by tau. So before going deep into the about shock waves, we should know what are the thermodynamic relations which gives the properties of the shock before and after the shock. That is before the shock and behind the shock. Because after the shock, the properties always changes. The thermodynamic properties like temperature, pressure, density, total pressure, total temperature, stagnant pressure, everything will change after the shock. So we know before the shock, every things are known. That is, we know the velocity, we know the pressure, we know the temperature. But after the shock, we don't know how much it is changing, because there will be a minor change or major change. Whatever maybe, we should find the changes. So based upon this thermodynamic relations only, we are to find the thermodynamic properties behind the shock. So thermodynamic relations, first of all, PV equal to, that is the gas equation, because here we are considering the gas and the value for the ratio of specific heat, gamma equal to 1.4 for air. So PV equal to MRT, V equal to 1 by rho. So therefore P equal to rho RT. So for a calorically perfect gas, this E internal energy, or we can write it as whatever maybe. You may study the notation. U means you just put it as U, or E means okay, E equal to mCV into T. So for unit mass, we will be considering as CV into T. So the formula becomes E equal to CV into T, and enthalpy, there is addition of heat to a particular medium, H equal to Cp into T. And also we know that gas constant R equal to, the value is 287. Depend upon the unit, it may vary, like 0.287, or you can consider as 287. Then we know the formula. It has another formula called R equal to Cp minus Cv, and also gamma equal to Cp divided by Cv. So we know this gamma is ratio of specific heats, and Cp is specific heat at constant pressure, and the Cv is specific heat at constant volume. So it has a specific value, that is Cp equal to 1.005 and Cv equal to 0.717 or 0.718, that we can consider like this. So these are the basic formulas. And also we know that forms of first law, del Q plus del W equal to del E. Then TdS equal to, that is Q equal to T into ds, and W equal to P into dV. Therefore TdS equal to dE, there is an internal energy, change in internal energy, plus P into dV. Therefore TdS equal to we know H equal to U plus PV. By substituting that, here TdS equal to dH minus V into dP. Also these are the so first we need to know what are the formulas for enthalpy, entropy, then isentropic relations. These things we need to know. This you have to by heart, or in a thermodynamics itself you may study all these equations, because with these equations only we can find the relation. Because if a shock is if suppose over the aerofoil or over the aerofoil a shock is formed means, or the surface of the aerofoil we have a normal shock means, the temperature will be T1, temperature will be T1. Then after the shock the temperature is T2. Same way, before the shock the pressure will be P1, and after the shock the pressure will be P2. And same way the conditions like for density also it will be P at rho 1, and after the shock it may be rho 2. But we know the T1 we are giving different notations and different names for both temperature means both have different values, both have a finite value. Because they are that have a finite value, that's why we are giving T1 and T2. We are giving a specific name for this. So in order to find, we know the value for T1. Suppose we are consider that we know the value for T1, but we don't know the value of T2. But and also suppose we know the value of P1 and P2 means, in order to find T2 we can just away take this relation, that is P2 by P1 equal to T2 by T1 per whole power gamma by gamma minus 1. This equation we found it from isentropic flow. We know the isentropic flow, PV power gamma equal to constant. The equation for isentropic flow is PV power gamma equal to constant. So in isentropic flow we have some three equations for PV, P and T, P and rho, P and V. Like we have some equations. By using this equations, we can easily find the values or the unknown values behind the shock or before the shock. Okay. So here the entropy. Yeah, we know the entropy is the unavailable energy that cannot be used. But if we know the formula for entropy, ds equal to del q divided by T. So if T increases, automatically the entropy is also increases. Entropy decreases, and the vice versa also happen. We know the second law. The second law can be classified like this one as a classist inequality and classist statement, and another one is Kelvin-Planck statement. Here the classist statement is there. So del ds less than or equal to del q, greater than or equal to del q divided by T. So one important consideration is the shock is a adiabatic process. So therefore, in adiabatic process, there is no additional heat is neither added nor rejected. Therefore, dq will be 0. So del q will be 0 for adiabatic process. Del q equal to 0. By substituting del q equal to 0 in this equation, it becomes ds will be automatically it will become 0. Therefore, for an adiabatic process, ds greater than or equal to 0. So for a calorically perfect gas, the change in entropy is, we have a formula for change in entropy, that is S2 minus S1 equal to Cp ln T2 by T1 minus R ln P2 minus P2 by P1. So if you know the ratio of pressure ratio and temperature ratio, we can easily find the entropy change across the shocks. So if you know the value of entropy before the shock, you can easily find the entropy change after the shock by using these relations. So please note this relations. That is P2 by P1 equal to rho 2 by rho 1 power gamma. That is equal to T2 by T1 power gamma by gamma minus 1. So for a note these things. For a steady inviscid adiabatic flow, the energy equation is H naught equal to constant. The enthalpy, stagnant enthalpy is equal to constant. For a, we know the enthalpy formula H equal to Cp into T. H equal to Cp into T. So therefore H naught equal to Cp into T naught. So if H naught is constant, then automatically T naught will be also constant. Therefore, for a steady, inviscid adiabatic flow, temperature will also, T naught will also, the stagnant temperature is also constant, or total temperature is also constant. So the energy equation for in steady inviscid adiabatic flow is H naught is constant. You know the formula for H naught is H naught equal to Cp into T naught. But if H naught is 0, automatically T naught will also become 0. Therefore, for a steady inviscid adiabatic flow of a calorically perfect gas, H naught is that stagnant enthalpy will be constant, and also the stagnant temperature is also constant. So I told that based upon the Mach number, we have classified that subsonic flow, sonic flow. So we know the Mach number m equal to v by a. The formula of Mach number equal to v by a. Here v is the velocity of the object moving, and a is the speed of sound. If the object is moving at a velocity, that is, the velocity will be at a, if the velocity is at a speed of sound means, then the value will be 1 by 1, or something that the value will be 340. Same, the speed of sound is 340 meter per second. Same, the object is also moving at the same velocity means, then by putting we will get 340 get cancelled, and the value will become 1. So this is how we will get. Then the if m equal to 1, then the flow is called sonic flow. Same way, if m is greater than 1, the flow is called supersonic flow. So in supersonic flows and all, the so everything, the Mach number, subsonic flow, supersonic flow, everything is adapted from the speed of sound only. Okay. So first of all, we should know what are sound waves. The sound waves are infinitely small pressure disturbance that propagate in a medium at a particular speed. So the sound waves which travels in a medium at a particular sound, and it is traveling at a velocity of 343 meter per seconds. Okay. Then the formula of so here we can see that disturbance or sound waves, the properties behind before the sound waves propagating are pressure P, temperature T, rho, density rho, and velocity of the wave is A. After the, if the sound is moving in a gas, then after that disturbance, the properties will be P plus dou P, T plus dou T, rho plus dou P, dou rho, and A plus dA. So by substituting this and by calculating the values, we will be getting A square equal to dP by d rho. We know from isentropic flows, we know that P by rho gamma equal to constant. So by substituting it, we will be getting A equal to, for the speed of sound, A equal to square root of gamma P by rho. But we know that P equal to rho R T. From that, P by rho equal to RT. Therefore, by substituting that, we will be getting A equal to square root of gamma RT. So the formula for speed of sound is A equal to, the notation is A, and the formula is A equal to square root of gamma RT.
Hello,
So,
hello, sir.
hello, yes.
Sir, previous slide.
Yes.
Sir, what is that figure A shows? A sound wave propagate.
Yes, that is from the derivation part. We don't need that derivation part, but I will explain that. So in the first diagram, the shock is moving from right to left. So, and first, so not shock, the sound waves. Okay, the sound wave is propagating from right to left, and initially the values are, the pressure before the before it is traveling is P plus dou rho, dou P, then temperature is T plus dou T, and this is a stationary waves. Okay. Then density is rho plus d rho. Okay. After that, when it is traveling after that sound waves, the properties of wave is pressure is P, temperature is T, and density is rho. Then right side we have this stationary sound wave, and that is moving in a gas. That is moving from left to right. Here, the left side diagram, it is moving from right to left, and here it is moving from left to right. So it is this stationary sound wave is moving at some particular velocity, and that is considered as A. And after some time, it will be the property changes to A plus d rho. There is a minor change in velocity. That is called dA plus dA. Sorry, d rho, not dA. Okay. So the first diagram, it is in a rest. Other thing, in the right side diagram, it is moving at some velocity. That velocity is the velocity. It is moving at a velocity of sound. So first of all, it is A. After some distance, that no, that sound will be after traveling to some distance, it will be the sound. It takes some time to travel now. That's why they are putting like A plus dA. Okay. So next is the main thing, shock waves. So we should know what is shock wave and how a shock.
Hello, sir. Hello, sir.
Hello.
Hello, sir.
Right. Yes.
Yes,
Yes.
that second figure is clear, sir, but not that first one. I'm not getting how it is like.
One second. One second.
In second figure cleared, sir, but
Yes. Yes.
figure A. But figure A, it's not clear, sir. Like how it is.
One second. One second. I will tell you.
Yeah, sure, sir.
So here in the left side figure, it is moving from left. That is a stationary or a stagnant gas. The gas is stagnant. That is not moving. The sound is emanating from one point. The sound waves are emanating from one point, and it's moving from right to left, not from left to right. Here, from left to right, it is moving from right to left. So the first time, the properties, it is not a. See, it is a stagnant. Stagnant means it is not moving. So before that, the property is P plus d rho, dP, and T plus dt. Actually nothing is here. See here, we may mention it like as P mean here in the yeah. See, in section 1 we will be considering as a P1, and section 2 considering as P2 more. No, likewise they are changing. After some time it becomes a P. After some time it becomes T. After some time it becomes P. After the propagation. Okay. Okay, then next thing is the sound shock waves. So shock waves are extremely thin region. That is of an order of 10 power minus 5 centimeter across the flow properties. So after the shock or beyond the shock, the flow properties change drastically. There is a major change in the flow properties. So suppose here you can see the two diagrams. One is the oblique shock, that is inclined to some angle, and another one is a normal shock. And we know other shocks are also there. There is a bow shocks. So if a shock is formed, means the what will happen? The air flows it will come, and it will concentrate at a particular point, and continuously the flow get concentrated at a particular point, and they form a thin layer. The thin layer is called shock wave, and because of the thin layer, that means if a body is moving at a particular at a supersonic speed, what will happen? I will explain. One second. See, there are two diagrams. See, one is subsonic flow, another one is supersonic flow. In supersonic flow, the velocity of the object is greater than the speed of sound. Suppose a object is moving at a velocity greater than the speed of sound, then it is called supersonic flow. Then what will happen? The object will move front, but the sound waves will be will reach our ear later only. So suppose it is a moving front, a layer is formed. That is here it is mentioned as a blue color. A layer formed. This is a thin layer which is formed because of the flow get compressed in a particular region or particular point. So that is called shock wave. And because of this, the flow upstream of the flows that don't know that this object is moving at supersonic speed. Once it hits the thin layer, then only it knows that something is moving at a supersonic speed. Okay. So we can see that properties of shock waves that we will be seeing later also. So before the shock, the Mach number is greater than 1. After the shock, the Mach number will be less than 1. And one more important thing is the flow across the shock wave is adiabatic. So you need to just note down this, because they may be asking whether the flow of a shock wave is adiabatic, isentropic. There's a question in some 2014 thing. One question is there. The flow is adiabatic, isentropic, isothermal, like this. The flow across a shock wave is always it is adiabatic only. Okay. So for a normal shock means it is inclined, that is perpendicular to the flow direction. That is 90 degree to the flow direction. That we'll be seeing later. But in this diagram, I am just explaining. For an oblique shock, the flow is the shock is inclined to the flow direction. So inclined to some angle. And as I told earlier, that the flow properties of properties changes after the shock. There is before the shock, maybe the Mach number is 1. It is greater than 1 means after the shock the Mach number decreases and it will become maybe m equal to 0.8. If it is 1.2 in before the shock means after the shock it will become 0.8. But we don't know that the value of Mach number after the shock. So what we need to do is, by using this derivative or equations and all, we need to find the properties downstream of the shock or after the shock or behind the shock. So next thing is the Mach cone, Mach wave and Mach angle.
Excuse me, sir.
Yes.
So can you please go back to the last slide, sir?
Yes.
So here it has been given as P01 or P03, sir. It is not visible properly.
Sorry, it is P01. Not
okay.
Not P03. It is P01.
In both the sides, it's P01.
Yes, P01 only.
Okay. Stagnation,
sir. Stagnation properties and all I have shown in another one slide that we will see there. Okay, no problem.
Is the enthalpy equal, sir?
Well, yes, stagnation enthalpy is equal.
Okay.
Stagnation enthalpy remains same throughout. Okay.
Okay.
Before the shock and after the shock, the stagnation enthalpy doesn't change.
Okay, sir.
There is a question from this also. They will be asking whether the stagnation pressure changes or they will be asking like this. State whether this statement is true or false. Which statement is true? Like this, they will be asking the questions. Okay. So in that they will be asking like this. After the shock, the temperature decreases. The answers will be the temperature decreases and the total pressure also decreases. Likewise they will be asking. But see, in oblique shock, what they have given is T2 is greater than T1 and also P02 is less than P1. So the answer will be temperature increases and also the total pressure decreases. Okay. That is the answer. So these are the flow properties. From this you need to know the flow properties after the shock and all. Just note it down.
So can you please give me a minute, sir? I'm just noting it down.
Okay. Or else in another one slide it is there. I can note it down from that. Note down from that. Okay.
Okay, sir. Okay, thank you.
Sir,
So yes.
hello, sir.
Yes.
Sir, flow across the shockwave is adiabatic. Whether it is like after the shockwave or in like while crossing.
Sorry. Whether
Yes.
I am audible? Yes. Okay.
Now you are audible.
Why they are mentioning the term adiabatic means we are not heating the shock, heating the flow and to produce some shock, or not. We are not not at all producing a shock artificially. Okay. Whether any heating process is there or any cooling process is there
No.
in the formation of shock?
No.
No. There is no heating or cooling process in the formation of shock. It's automatically, if a body is moving at a supersonic speed, automatically shock get formed because of the compression of air flow at a particular region. Okay. Continuous compression of yes.
In second region where high temperature, no, sir. T2 is greater than T1.
Yes, T2 is greater than T1. See, if pressure increases, no. See, that what I am telling is temperature change is no problem, but we are not at all giving any external input to heat flow and produce a shock. We are not at all doing that. Okay, automatically the air get compressed, because if pressure is increased, automatically what will happen? Temperature will also increase. We know P equal to rho RT. Pressure increase means temperature will definitely increase. So based upon that only they are giving. See, pressure is after the shock, the pressure is increasing. Because of that, there is a small change in temperature also. Okay. Okay, fine. So next thing is Mach wave, Mach cone, and Mach angle. So first of all, we should know what is Mach line. So see here, there is a blue color line is there now. This blue color line is called the Mach line, because this is the place where all the pressure disturbance are concentrated, or the flow is flow get compressed, or airflow get compressed, and there is a pressure layer formed. This pressure layer is called Mach line. Then second thing is the Mach wave. Mach wave is a pressure wave traveling with the speed of sound caused by a slight change in pressure due to a compressible flow. Okay. Then third one is the Mach angle. Mach angle is the angle between the flow direction and the Mach line. Then so this Mach angle is sin mu equal to, so here you can see the angle of angle between the Mach line and the flow direction is mu. So therefore we know this direction is ut and opposite side is at. Therefore sin mu equal to at divided by, here you can see this, sin mu equal to at divided by vt. Tt get cancelled. So therefore sin mu equal to a by v. So we know that m equal to v by a. So therefore the equation becomes sin mu equal to 1 by m, or then mu equal to sin inverse of 1 by m. Sin inverse of 1 by m. Okay. So Mach angle is mu. Mach angle is the angle between the Mach line and the flow direction. So next thing is the left running wave and right running wave. Whether you have seen any left running wave and right running wave in your experiments and all, lab experiments and all, or in any books and all books, whether you have seen. Have you seen the shock inside a nozzle and all?
So I've heard about only two waves, compression and then expansion.
Yes, compression waves, that is formed because of the compression corner, and expansion wave formed at the expansion corner.
Yes, sir.
So both waves are there. Left running wave means
left running. No, sir, I have not come across this word.
Yes, but you may come across, but you may not remember, because you have seen this supersonic flows inside the shock wave or supersonic tunnels and all. The shock which moves left side of the flow, left side is called left running wave, and the shock which moves right side is called right running wave when viewed from front view. In the front view, if you are viewing from here, the shocks, because of the in the, if you are seeing from the front means in the test section and all, you will be seeing now in the glass we are seeing means the shock will be found like this only. So consider this is a test section. See, this is a test section, and see here we are keeping an object, and this or here we can keep an aerofoil over this. In the aerofoil, consider this is the shock formed, a thin layer formed over the surface of the air. If you are viewing from in the front, you will be seeing the waves like this. This is left, and this is the right. Okay. So waves which shock waves which moves left side is called left running wave, and which moves right side is called right running wave. Okay. That these things and all we will be seeing in Mach reflection, interaction of shocks. In the topics we will be seeing this much detail. Okay. Then next thing is the zone of silence and zone of action. So we all know Mach cone. I haven't explained that Mach cone. So here see this. There are two lines. One is a left running line, and another one is a right running line. All the whole we when we picturize this line, it is like a in the form of a cone. This cone is called Mach cone. Okay. All the whole we when viewing from front, we can see this is this Mach lines are like Mach cone. So our the propagation will be also in the form of cone only. Okay. So it is called Mach cone. Everything, the region inside this Mach cone is called zone of action, and the region outside this Mach cone is called zone of silence. Okay. And here we can see the on 4 pictures, like one. The first one, you can see the Mach number is 0. That is object is at rest. So the propagation will be like this. And in the second one, the Mach number is that is the object is moving at a subsonic speed. When it is moving at a subsonic speed, it somewhat the propagation. We can see the propagation from the first picture. There is a small change in the second picture. When we are moving at a zonic speed, what will happen means from the object only the propagation starts. If you are moving beyond sonic speed, that is at a supersonic speed, object will move front, but the disturbance will be formed later. This is the formation of that is the speed of sound is the sound is traveling at lesser speed, but the object is traveling at faster. Object is traveling little bit faster. So now we will be seeing what is normal shock. Then after this, we will be seeing that we have some derivations for derivative terms and some formulas for this normal shocks, and we will be solving some problems regarding this normal shock. After that, in the next session, we will be seeing oblique shock and all. Okay. So here we can see the flow properties. M1, before the shock, the flow properties are like, or consider this is a normal shock which is stagnant. That is, it is not moving. So the right side section we will be considering it as 2, and the left side it is we will consider this section as 1. So in the first region, the flow properties in the first region is M1, P1, T1. That is M1 is a Mach number, pressure, temperature, density, and velocity. Same way, after the shock, the properties are M2, P2, T2, ρ2, and U2. So in one diagram I have shown some values after the shock. What will be happen for a normal shock? What will be happen means Mach number decreases after the shock. Also, velocity decreases after the shock. Pressure, temperature, it increases. If a pressure is increased, automatically temperature is also increased. There is a small change in entropy also. Therefore, entropy also increases. But the total enthalpy, it remains constant. And also, the total pressure, it decreases. The total pressure decreases. So in oblique shock, the oblique shock also, Mach number is reduced. But what is the difference between normal shock and oblique shock is, in normal shock, Mach number will be decreased to subsonic level. That is, after the shock, the Mach number M2 will be in subsonic, maybe in 0.8, 0.7, 0.9, like that. But in oblique shocks, the M2 will be still remains in supersonic speed only. And the velocity and Mach number decreases, automatically velocity decreases. And we know the pressure after the pressure increases. So if pressure is increased, density will be increased, temperature will be increased, other all things is remains same. Only thing is, after the oblique shock also, the Mach number, it still remains in supersonic only. That means if you are having supersonic speed, Mach number is that is equal to 2, and after the oblique shock, the Mach number will become 1.1, 1.2, like this. So now we'll be seeing in detail what is normal shock. So here two diagrams are there. One is a blunt shape of a body. Upstream of the body, a shock is formed. They are saying it is a bow shock. If the shock is curved, then the shock is called bow shock. But if the shock is curved also, there will be a normal shock. Do you agree with my statement? I'm telling this.
Can you
blunt
please
body,
repeat it, sir?
Yes, I will be repeating that. See here, blunt body is there. Upstream of the body, there is some flow, and because of the flow, there is a shock formed in front of the body, and the shock formed is a bow shock. But I am telling telling that, in spite, if the shock is bow shock also, it has a normal shock. The normal shock will be in the flow direction, near to the flow direction. Whether it is true or not.
So is the normal shock formed in front of the bow shock, or ahead of bow shock, or before the bow shock?
No, in the bow shock, not ahead, not beyond. It is formed in the bow shock. Actually, see, consider a tube like this. Okay. See, now we are considering a tube like this. Okay, simple. If you are considering a tube like this, I am taking. We know in aerodynamics and all. If you want to calculate the properties of flow properties or some properties in our own area, we should draw a control volume, right? So what we are doing, I am doing here. I am taking a control volume, and first time, if I am taking a control volume over the particular area, that area will be what? It is curved, or it will be like I am zooming the stream tube and taking a small control volume. And if I am taking like that, it will be the stream tube will be like this. Okay, am I right? You didn't understand, I think so. Okay, fine, I will explain once again. See, you have a picture in your mobile phone. Okay, what will happen? What is happening when if you are zooming the picture too much? If it has 100% zooming means, what will happen? What is happening?
The pixels will be reduced, sir.
Pixels will be reduced. Actually, if the shape of your if the picture is about your picture, okay, so the picture is your photo, and while zooming, what will have you can see square pixels, correct?
Yes, sir.
Or the same way here, the stream tube is curved, but I am not taking the whole stream tube. I am taking a small portion of that stream tube. If I am taking a small portion, what will happen? What is that? That portion is straight only. Okay, it will be like this only. It won't be curved at the particular region, because I am taking small portion. I am zooming the whole stream tube and taking on small control volume. That small control volume is like this. Okay, so in the bow shock also, the bow shock, consider this bow shock is a stream tube. This is like a stream tube, and in the region I am taking a small area. That means in the flow direction, here I am taking a small area. Here if we see that small area, the shock is perpendicular to the flow direction. If a shock is perpendicular to the flow direction means it is called normal shock. That means the angle between the shock and the flow direction is 90 degree. If it is in 90 degree, then it is called normal shock. Okay. Did you understand?
Yes, sir.
Okay. What I am telling is just zoom the pulse shock, and I am taking a small region over the shock and near to the axis line, this axis line. So in this axis line, the angle of the shock is perpendicular to the flow direction, or perpendicular to the axis line. If a shock is perpendicular to the axis line means what is, then the shock is called normal shock. Okay. So whatever if a bow shock is also there at the region of a center or a region to the flow direction, the shock will be normal shock. After that it will become curved and it will become a bow shock. Okay, so here it will be normal shock, here it will be a bow shock. Okay, and the second thing is a shock in nozzle. So shock in nozzle, we know the before the shock the Mach number is greater than 1. After the shock, the flow properties changes, that we will be seeing in the next things also. Major assumptions for normal shock is the flow should be steady, the flow is adiabatic, there is no viscous effects, and there is no body forces. Based upon these assumptions only, we can derive the equation. Okay. The flow is steady means dou by dou t is equal to 0. Okay. So if the flow is steady, dou by dou t is equal to 0. And second thing, the flow is adiabatic. That means there is no heat entering or leaving the system. And the third thing is there is no viscous effects. That means the shock is the flow should not have any frictional effects or shear stress effects in the control volume. Okay. Then fourth thing is there is no body forces. That is in energy equation and all, we should neglect the body forces. Okay. So main thing, we have three equations. One is continuity equation, second one is momentum equation. These are the three basic equations. The third one is energy equation. Based upon these equations only, we are going to derive this normal shock derivation. So first of all, continuity equation.
Sir?
Yes?
Sir, I have a question in that assumption slide. Whether we are assuming the flow to be adiabatic, or will there be any change in heat? Or just we are assuming the flow to be adiabatic?
Actually, the flow is adiabatic only. But before derivations and all, we should we need to assume it. Okay. Because see, normally shock won't form because of any heat addition and all. Normally it will form. Okay, we are not giving any we're not applying any current or electric current to heat the gas and form a shock. Normally it is if a body is moving at supersonic speed, automatically the shock is formed. So that's why the flow is adiabatic, because there is no change in there is no heat addition or heat rejection. Okay.
Yes,
normally in thermodynamics, what we will do, we will be supplying some heat from a source, or we will be burning the gases and we are supplying by because of the burning the heat is supplied to the gas. But here we are not at all adding heat to the gas or heat to the air. Okay.
Okay, sir.
Suppose we are adding the heat means then the flow will be
Hello, sir.
Suppose we are adding some heat to the system means then flow is not adiabatic. Okay.
Adiabatic. Okay, sir.
Then, so based upon these three equations only, we are going to derive the normal shock equations. So first one, for continuity equation, rho 1, we know the properties like before the shock. Considering properties are a flow are P1, rho 1, T1, M1, U1, then P01, H01, T01, S1. Same way, after the shock, the condition is 2. So therefore, I'm considering like P2, rho 2, T2, M2, U2, P02, H02, T02, and S2. You know the expansion of P1 and all that. So I'm skipping that. So for a continuity equation, rho 1, since this is a stream tube, we can consider like consider this is a stream tube. In the stream tube, we are having a shock which is normal to the flow direction. So if it is normal to the flow direction, it is called a normal shock. And we know this, the how much flow is entering, it may leave the exit, because it is considered it is a stream tube. So therefore, from continuity equation, rho one a1 v1 equal to, or v1 here we are considering as u1. So therefore, rho 1 a1 u1 equal to rho 2 a2 u2. But the area is same. There is no change in area. Therefore, rho 1 u1 equal to rho 2 u2. Same way, momentum equation also, p1 plus rho 1 u1 square equal to p2 plus rho 2 u2 square. Same way, energy equation, p1 u1 plus rho 1 u1 plus u1 square by 2 into u1 equal to p2 u2 plus rho 2 into e square plus u2 square divided by 2 into u2. Now what I am doing is, I am dividing the above equation by rho 1 u1. So after dividing that, rho 1 u1 p1 by this u1 get cancelled. So therefore, equation becomes p1 by rho 1 plus, here also rho 1 is there and u1 is there, both things get cancelled. Therefore, equation becomes e1 plus u1 squared by 2. Here also it will become p2 plus p2 by rho 2 plus e2 plus u2 square divided by 2. Just I am dividing the rho 1 u1 terms in both sides. So we know h equal to u plus pv. Here it is u plus pv. Here it is the u is internal energies. Here I am mentioning it as E. Therefore, E plus pv, v equal to 1 by rho. Therefore, p by rho plus E equal to, I am mentioning it as h1. So therefore, h1 plus u1 square by 2 equal to h2 plus u2 square divided by 2. So the equation is h1 plus u1 square by 2 equal to h2 plus u2 square divided by 2. So another one thing here we will be seeing like this. This is the energy equation for h1 plus u1 square 2 by 2 is the energy equation for adiabatic flow. But in thermodynamic relations, we have seen that h1 plus h plus u1 square by 2 equal to constant. Likewise, we will be seeing that, we will be seeing in the next slides and all. So for a perfectly calorically perfect gas, we know h equal to Cp into T. So h equal to Cp into T. Therefore, by substituting that h here, it is h1. Therefore, I am mentioning it as C1 Cpt1. Therefore, Cpt1 plus u1 square by 2 equal to, for h2, I am mentioning it as putting the term T2. Therefore, Cp into T2 plus u2 square divided by 2. Then for Cp, we know the formula for Cp equal to gamma R divided by gamma minus. Cp equal to gamma R divided by gamma minus 1. So by substituting that, the equation becomes gamma R T1 divided by gamma minus 1 plus u1 square divided by 2, that is equal to, same way for Cp T2, Cp I am substituting gamma divided by gamma minus 1 plus u2 square divided by 2. We know that gamma RT, we can substitute it as a square. A square equal to a equal to square root of gamma RT. Therefore, a square equal to gamma R T1. So I am substituting here like this. So a square divided by gamma minus 1 plus u1 square divided by 2 equal to a2 square divided by gamma minus 1 plus u2 square divided by 2. Okay. Now, in order to find the stagnation conditions and all, what I am doing is, I am fixing a point. Maybe we can fix the first point itself, stagnation point. But I am now here, I am considering like this. If the point 2 is stagnation point, then A will be equal to A0 and U2 will be equal to 0. So therefore, these equations a by gamma a square divided by gamma minus 1 plus u square divided by 2 equal to a naught square. This here substitute here this equation a2 equal to a naught and u2 equal to 0. So this u2 term, it will become 0. Then this a2 term, we are substituting the value a naught. So a naught square divided by gamma minus 1. So therefore a1 square divided by gamma minus 1 plus u1 square divided by 2 equal to, same way, if a1 square, then we can substitute like this 0.2 as 0.1 as a stagnation point, fix 0.1 as a stagnation point.
Excuse me, sir.
Yes.
So when we are substituting that a is equal to a naught, we can just say that it has to be a itself, no sir. The y in RHS has been put a naught then.
Actually, this a naught, a equal to a naught, I am substituting like this. See this in this equation,
like
a
I'm asking like a1, a2 all are equal to a sir.
Yes.
Then
Totally, totally. Actually, take anyone equation. Say a2 square divided by gamma minus 1 plus u2 square divided by 2. Anyone side. Take anyone side and fix that this point is stagnation point. Then the equation becomes a equal to a naught. Then all the whole it will become an equation now.
Oh, no. I'm not asking about the stagnation points. Any one point we are fixing on any side, and then we are just substituting. But I'm asking,
yes,
like we can just put a no, sir. But why a naught has been put there? So because it is equal, right?
Actually, naught represents the stagnations. I'm just changing the values from a to a naught. That a naught represents it is a stagnation point because the velocity is 0 at that point. Therefore, I am considering as a naught.
Okay.
And also the velocity also for u2 is a velocity that u2 will be equal to 0 because there is no velocity. It is a stagnation. Therefore, u2 equal to 0. Then we will substituting that it becomes u2 square. The whole term will be 0. So therefore, the equation becomes a1 square divided by gamma minus 1 plus u1 square divided by 2 equal to a2 square divided by gamma minus 1 plus u2 square divided by 2 equal to a naught square divided by gamma minus 1, that is equal to constant. So this is the equation. Then first I substituted that I fixed the point as a stagnation point. Now I am fixing the point as a equal to a star, then u will be equal to a star. This a star means we know that a characteristic Mach number, that and all we will be seeing later, but now just I am saying, see, we know the m Mach number equal to p by a. Okay. Suppose this velocity of the object is moving at a same speed of sound, means then what will happen? We will be getting the value as 1. So if v equal to a, then we will be getting Mach number equal to 1. Okay. So this if if v equal to a for a sonic value, then we will be considering that as a characteristic Mach number. So I am mentioning that as m star. M star equal to v by a star. That is a equal to a star. Okay. So m star equal to v by a star equal to 1. So then I am substituting as a equal to a star and u equal to the velocity is also that is equal to a star because same only now. So therefore, in the above formula, what I am doing is I am substituting a equal to a star. So I am substituting that u a square divided by gamma minus 1 plus u square by 2 equal to, here it will become for a star square divided by gamma minus 1 plus, but we know that u is not 0 here. U will become a star. Therefore, by substituting that, it will become a star square divided by 2. All the whole, by solving, we will be getting gamma plus 1 divided by 2 into gamma minus 1 into a star square, like this. See, that is equal to a star all the whole comma a star square into 2 plus gamma minus 1 divided by 2 into gamma minus 1. Gamma minus 1. So this 1 here cancel and it will become 1. So gamma plus 1 divided by 2 into gamma minus 1. That's why, that's what I am substituted here. Then, so if we have 2 points, now I'm first here I am what I am considering is I am having only 1 point at this streamline. Suppose we have 2 points, means we can split that as a1 and a2. So therefore the equation becomes a1 square divided by gamma minus 1 plus u1 square divided by 2 equal to a2 square divided by gamma minus 1 plus u2 square divided by 2 equal to same previous formula, gamma plus 1 divided by 2 into gamma minus 1 into a star square, that is equal to constant. Okay, so now see here we have one equation, and also here we have another one equations. Both equations in the left hand sides are equal. By equating these two equations, we can relate this a0 and a star value. So by relating that, we will be getting gamma plus 1 divided by 2 into gamma minus 1 a star square equal to a0 square divided by gamma minus 1, that is equal to constant. So we want to find the value for a0 and a star. Any relations or any formulas they are asked, means you need to substitute this formula and solve the problem. Okay. Also, we know that h plus u from energy equation Cp T plus u square by 2 equal to Cp into T naught. Same way, by considering there we have 2 points in the streamline, we will be taking like this: Cp T1 plus u1 square by 2, that is equal to Cp T2 plus u2 square by 2 equal to Cp into T naught, that is equal to constant. Okay. So after solving things, we will be getting like for T naught by T equal to 1 plus u square divided by 2 into Cpt, that is equal to Cp value gamma r divided by gamma minus 1. Then gamma rt, it will become a square, gamma rt equal to a square. So u square by a square, we will be substituting as m square. So therefore the formula for T naught by T equal to 1 plus gamma minus 1 divided by 2 into m square. Also, we know from isentropic relations, P naught by P, that means P2 by P equal to rho 2 by rho, like this. Isentropic relation, you know, P2 by P1 equal to rho 2 by rho 1 power gamma whole power gamma, that is equal to T naught by T, sorry, T2 by T1. Same way here I am considering for values for stagnation and static. That's why I'm putting values like T naught by T. That T is for static and T naught for stagnant. Okay. Or stagnant, they will call it as total temperature. So total temperature to static temperature. The formula is T2 divided by T1 or T naught divided by T whole power gamma by gamma minus 1. Okay. So by substituting it, we will getting values for P naught by P and rho naught by rho. Okay. So P naught by P equal to 1 plus gamma minus 1. See, please note these 3 formulas. This one formula and these 2 formulas, because this is most important for us. Have we noted down, guys?
Just a minute, sir.
Okay.
Yes, sir. Noted down.
Okay, fine. See here, this equations we have a value called Mach number. Okay, If you know the Mach number value, we can Mach number and gamma value. Gamma value for air, we are considering it is for air only. So here the gamma value is equal to 1.4. Gamma equal to 1.4. So 1.4. So by substituting the value for gamma in this equation, and if you know the Mach number value, suppose in your question they have given the Mach number equal to 0.8 or 1, consider it as 1. Then by substituting it, we can get the temperature ratios now. Total temperature to static temperature ratio we can get, right? So if we know the Mach number value, we can find the ratios of stagnant to static temperature, and also stagnant to static pressure, and also stagnant to static density. Okay, here that's what I have done. I'm substituting m equal to 1. So after substituting m equal to 1, the equation becomes T star by T naught equal to 2 divided by gamma plus 1. Same P star by P naught equal to 2 divided by gamma plus 1, the whole power gamma by gamma minus 1. And rho star by rho naught equal to 2 divided by gamma plus 1, whole power 1 by gamma minus 1. Okay. And if we substitute the value for gamma, we will be getting this values. Please by heart these answers, or if you know the formula, no problem, or else just by heart these values, because in your problems and all, they straight away and we can substitute these values and we can find the characteristic values, that is characteristic temperature, characteristic pressure, and characteristic density for all these things. Okay, why we are putting star means for a Mach number m equal to 1, we will be m equal to 1, the velocity will be, the speed of sound is equal to a equal to a star. Then the Mach number is called as characteristic. This a star condition means it is called characteristic Mach number. If it is a star is mentioned means then the Mach number is equal to 1, and also all condition the Mach number won't change. That is a sonic condition, or in a nozzle they will consider it as throat condition. Okay, in throat the Mach number will be equal to 1. The surface means the surface of the aerofoil where the Mach number is 1 is called sonic conditions, and the point at which it becomes 1 is called, the Mach number is called characteristic Mach number, and the velocity at the Mach number is 1 is called characteristic velocity. So here T star by T naught equal to 0.833, and also P star by P naught equal to 0.528, and rho star by rho naught equal to 0.634. Okay, so here this is the definition: m star equal to u by a star, and by substituting that we are getting this. Already we got this formula. So in this formula I'm dividing this by u square. So u square, when I divide the above equation by u square, it will become a by u the whole square divided by gamma minus 1 plus u square by u square. It will get cancelled and it will become 1, and the right hand side a star by u the whole square. Okay, so a by u means m equal to v by a. You know, m equal to a, so this here it will become 1 by m square, and here it will become 1 by m star. So from this, by solving this, we can get m square equal to 2 divided by gamma minus 1 divided by m star square minus gamma minus 1. This equation and this equation is important. Please note this also. So m star square equal to gamma plus 1 into m square divided by 2 plus gamma minus 1 into m square. So in order to find the characteristic Mach number, or in order to find the Mach number, we can use this characteristic Mach number formula. By substituting this value, we will be getting m square value. Okay, so we will be solving one formula, then we will be we can go through this derivation. So shall we solve this problem? Anyone please reply?
Yes, sir.
Okay. because too much of derivation is also not good. So we will be solving this problem. After that, we can go through that derivative part. Okay. So here, what they have given is calculate the Mach number at any point in a flow. We should calculate the Mach number at any point in a flow where the temperature is 320 Kelvin. They have given the temperature and velocity 1000 meter per second. So shall we calculate the Mach number? Anyone? So the given data is temperature is given
2.7, sir.
2.7. Super. So for calculating the Mach number, we know m equal to V by A. So this is what we studied in our last sessions. That is m equal to V by A. Speed of sound equal to Mach number equal to in question itself they have given the value of velocity. So we need to find the value of A. That is equal to square root of gamma R into T. So the answer is by substituting, we know that R gas constant, that is a 287, then gamma 1.4, and temperature is here they have given 320 Kelvin. By substituting this in this equation, we will be getting m equal to, what is the answer? M equal to
2.78.
78, sir.
78. Okay, super. Okay, fine. Okay, fine. So shall we solve this problem? This is the problem is based upon our previous derivation only. So it is a ways for us to solve this. So here consider a point in an airflow. Here also we are considering a point in an airflow where the local Mach number, they are given Mach number, local Mach number, static pressure, static temperature are 3.5. So the Mach number is 3.5, static pressure 0.3, and static temperature is 180 Kelvin. Calculate the local values of P0, T0, T star, A star, and M star at this point for M equal to 3.5. So this is conditions for M equal to 3.5, P0 by P equal to 76.27, T0 by T equal to 3.45. So it is easy for. Have you noted down the formula for this T0 by T, everything and all? Have you noted down that? So what you have to find is, you have to find the P0 value, T0 value, T star value, then A star value, then finally M star value. Okay. No need to change the pressure values, that is 1 atmospheric into bar or something and all. Just keep it as same. That is in atmospheric value unit only. Please solve the questions and tell the answers. If you have any doubt, means you can ask me. The given data are the easy only. We have P0 by P value is 76.27, T0 by T value is 3.45. If you don't know the value, means only it is somewhat difficult, but you know the values, so that you can easily find the remaining answers. Students, hello. Whether you guys are solving?
Sir, P0 value 22.881.
P0 value, once again. P0 value 22.88. Correct only.
T
So
naught value
22.
621.
22.8. T naught value?
621, sir.
621.
620. And M star 12.25.
What? M star? M star?
12.25, sir.
12.25.
So T star value I'm getting 887 Kelvin, sir.
887.
T star I'm telling, sir.
No. What are you getting?
517.5.
One second, sir. I think I made a mistake.
Sir, T star is 517.5.
Yes, T star equal to T star. Okay, sorry. So T star equal to 517.5.
5. Yes, sir.
Okay.
Sir, A star is 456.4.
A star is 456.4. Okay, correct only. Then A value? Then sorry, M star value?
$2.06.
Yes, M star value 2.06. M star equal to. Others all, yeah. You get these answers? 2.06. Okay. Everyone got these answers?
Yeah, yes, sir.
Okay, fine. So this type of problems they won't ask for your in your gate exam and all, because this is for your understanding. Because we have seen on derivation and we have seen a lot of formulas. So based upon that formulas only we are so in order to understand how to use that formulas only I'm given this problem. Okay, so anyone please answer this question. Normal shock wave can occur in A, subsonic flow, B, supersonic flow, C, subsonic with compressible flows, D, both subsonic and supersonic flows.
Option B, sir.
Option B, because normal shock wave will occur only on supersonic flows. Okay. So other all things we can see later because I don't have time enough time. So we have seen some formulas for normal shock waves. That is how we can calculate a Mach number and the characteristic Mach number based upon the normal shock wave, and how we can calculate the stagnation and the stagnation temperature and the static temperature ratios and the stagnation and static pressure ratios, density ratios based upon the Mach number. Now we need to we are focusing on the change in property after the shocks, because we know that if before the shock maybe the property is m1 for Mach number, and after the shock somehow it is changed. We know that it is changing. We should know how it is changing and how we can find the change. So in order to do that, we are going with some series of equations. So here also this 5 equation, it is common. So first one for normal shock wave, we are considering a continuity equation, that is rho1 u1 equal to rho2 u2, and momentum equation p1 plus rho1 u1 square equal to p2 plus rho2 e2 square. Same way energy equation equal to h1 plus u1 square divided by 2 equal to h2 plus u2 square divided by 2. In the same way, we know that for a calorically perfect gas, h2 equal to not h2, h1 also we can put. Here I am just considering h2 equal to cp into t2. Then by dividing this equation 1 and 2, we will be getting like p1 by rho1 u1 plus u1 equal to p2 by rho2 u2 plus u2, that is equal to, by solving this u2 u1 I am just taking to right hand side, and p2 by rho2 u2 I am just considering bringing to left hand side. So p1 by rho1 u1 minus p2 by rho2 u2 equal to u2 minus u1. We know p by rho equal to gamma p, a equal to square root of gamma p by rho. That means a square equal to gamma p by rho. So by substituting it here, it will become a1 square divided by gamma into u1 minus a2 square divided by gamma into u2, that is equal to u2 minus u1. We have a formula for values for a1 square and a2 square in the last derivation. I'm showing the values here. That is a1 square equal to gamma plus 1 divided by 2 into a star square minus gamma minus 1 divided by 2 into u1 square. In the same way, a2 square also we are having this equation. By substituting this equation and this a1 square and values, a2 square value in this equation, we will be getting gamma plus 1 divided by 2, gamma plus 1 divided by 2 a star square divided by gamma u1 minus gamma minus 1 divided by 2 gamma u1 minus same for a2 square substituting the value. Therefore minus gamma plus 1 divided by 2 into a star square divided by gamma u2 plus gamma minus 1 divided by 2 gamma u2, that is equal to u2 minus u1. So here also we have u1 u2 as a common. So therefore by taking u2 minus u1 as a common, gamma plus 1 divided by 2 gamma u1 u2 into u2 minus u1 a star square plus gamma minus 1 divided by 2 gamma into u2 minus u1 equal to u2 minus u1. So u2 minus u1 get cancelled. So therefore equation is reduced to gamma plus 1 divided by 2 gamma into u1 u2 a star square plus gamma minus 1 divided by 2 gamma equal to 1. So by solving this, we can get, see here, gamma plus 1 divided by 2 gamma u1 u2 into a star square, so I'm putting as a square, equal to minus of 1 divided by, or just cross multiply this, and we can bring to that side. So by cross multiplying it, 2 gamma into here it will come into 2, sorry, into u1 into u2. So into u1 u2 equal to 1 it will come. So that by cross multiplying this, it will come like this, that is equal to 2 gamma in this one. By cross multiplying it, it will come 2 gamma into u1 u2. So after solving it, we will be getting like this, a star square equal to u1 u2. So this is the Prandtl relation for normal shock wave. So the Prandtl relation for normal shock wave equal to a star square equal to u1 into u2. So a star square equal to u1 into u2. So from this, again I am cross multiplying here. So it will become 1 equal to u1 divided by a star u2 divided by a star. So u1 divided by a star equal to, I can write like this, m1 star, and u2 divided by a star I can write like m2 star. So therefore, yeah, from this m2 star equal to 1 divided by m1 star. Now I'm substituting the value for m1 star, and because we know the value for m star, so by substituting the value for m star here, see here m star equal to gamma plus 1 into m square divided by 2 plus gamma minus 1 into m square. So if it is a m1 star, means here m1 star equal to m1 divided by, here also it will become m1. Suppose it is m2 star, means here it will come m2 square divided by m2 square. Okay, the same manner I'm applying here. So therefore, by solving it, we can get m2 square equal to 1 plus gamma minus 1 divided by 2 into m1 square divided by gamma m1 square minus gamma minus 1 divided by 2. So from this equation, we can get, if we know the value of m1 square, value of Mach number before the shock, that is upstream of the shock, we can find the value of Mach number downstream of the shock. So here, this is a shock. Consider this is shock. This is upstream of the shock. The value is m1. Downstream of the shock, the value is m2. Suppose we know the value of this m1. M1 value we know, means we can find the unknown Mach number m2 by using this equation. So m2 square equal to 1 plus gamma minus 1 divided by 2 m1 square divided by gamma m1 square minus gamma minus 1 divided by 2. Okay. Then another one thing, this is also important thing. If m1 value is infinity, then by substituting it, the equation is reduced to a finite value, so that we can get Mach number is equal to m2 is equal to 0.378 for a normal shock wave. These are the thermodynamic relations.
So once again, can you go to the previous slide, sir? I just see the value. It's 0.378. Okay, sir.
Yes, 0.378. Please note down, everyone note down. I'll be showing on a problem regarding this. At that time, you will understand why I am stressed to note down this value. Okay. So the thermodynamic relations we know from continuity equation, rho 1 u1 equal to rho 2 u2. From that, rho 2 by rho 1 equal to u1 by u2. So from that, you'll be getting that is equal to u1 square divided by a square, that is equal to m1 star square. Same way, rho 2 by rho 1 equal to u1 by u2 into, that is equal to gamma plus 1 into, and that is, this is the formula. Substituting here. Same way, p2 by p1. These are the relations, and after solving, we are getting these three formulas. So for in order to find the pressure ratio, we need to use this equation. In order to find the temperature ratio, we need to static temperature ratio. We need to use this equation. For enthalpy also, we can use this relation. Enthalpy ratio also. For density, we can use this relation. Okay.
So can you give us some 2 minutes time, so I will note this down.
Take your time. No problem. one more thing I am telling. See here, consider this is again consider a shock wave, normal shock wave. So in every problem, they will give the value for M1, P1, T1, and sometimes ρ1 also. So if they have given the value, then sometimes velocity also, v1 also they will give. Suppose you know the velocities, and if you know the by knowing the value of m1 also, we can easily find the value for here. See, pressure ratio P2 by P1 equal to 1 plus 2 gamma divided by gamma plus 1 into m1 square minus 1. This is the formula. So here the unknowns are only thing, the unknown is m1 square. So initially, if in your questions they have given the value for Mach number, initial Mach number means, easily we can substitute in the Mach number in this equation, and we can find the value for the static pressure ratios. And also, if they have given the value for pressure P1 means initial pressure means, by substituting in this value, in this formula, we can easily find the value for the final pressure. That is after the shock, the pressure value, we can find it. So this is how we need to find the values. Okay. Have you note down?
Yes, sir. Noted down, sir.
Yes. Thank you. So for gamma equal to 1.2, we have some certain values, and for if m1 is the limit, m1 tends to infinity means the Mach number, final Mach number value is equal to 0.378. So 0.378, and also pressure density ratio P2 value, sorry, ρ2 value, it is equal to 6. And same way, pressure value, it will become infinity. Then temperature value, it will become infinity. Temperature ratios, it will become infinity. Okay. And also, please note down this, the entropy value across the shock is, entropy increases across the normal shock. So S2 minus S1 equal to minus R ln P02 divided by P01. So from that, the pressure ratio, stagnant pressure ratios, P02 divided by P01 equal to e power minus S2 by S1 divided by R. So please note down this 6 formulas. This is very important for you. They will be asking questions like, suppose m1 is equal to infinity, or they will asking like some asymptotic value. Then we need to put m equal to infinity, and we need to find the answers. Suppose they have given any questions means, you need to straight away you can write this answer. No need to solve any equations and all. Okay. Please intimate me when you finish noting down. Everyone finished? Nice.
I finished it, sir.
Okay. Okay. So see here in the thermodynamic relations, anyone noted that the pressure values, that is pressure ratios, temperature ratios, and density ratios, it is changing because of, it is a function of what? One is gamma, and another one, it is a function of,
Mach number.
yes, Mach number. So the normal shock, the temperature ratios, pressure ratios, and density ratios, it is a function of Mach number alone, not gamma, because gamma is a constant value, so we won't consider that. So the pressure ratios, temperature ratios, and all everything, it is a function of Mach number only. So therefore, a normal shock is a function of Mach number only. Okay. Okay. Shall we solve this problem? So they have given on what they have given is, for a normal shock, the relation between upstream Mach number m1 and the downstream Mach number m2 is given by m2 square equal to 1 plus gamma minus 1 divided by 2 into m1 square divided by gamma m1 square minus gamma minus 1 divided by 2. For an ideal gas, gamma equal to 1.4. The asymptotic value of m2 is, we need to find the value of m2. Shall we find? Any idea of finding this value? Anyone? Previously only I explained.
So the meaning of asymptotic here, sir?
That's what I am telling. That is a asymptotic value is they are representing it as a infinity value. Okay. So if
0.378, sir.
yes, suppose the max Mach number is here they haven't given any values. Okay, the asymptotic value is when we will get a different value while the upstream Mach number is some upstream Mach number have some value. Okay, I told that if for a ideal gas, that is gamma equal to 1.4, if the Mach number upstream of the shock is infinity, if it is infinity, then we will get the downstream Mach number value a different value. Okay, so therefore the value of m2 is 0.37. What 0.372? I think so. 0.378. Sorry,
0.378, sir.
0.378. Okay. Okay. Next problem we have solved already. This is also we have solved. So for this, you have told the answer that normal shock wave can occur only in supersonic flows. The next, in a normal shock wave, the static properties are function of. Can anyone tell the answer? In a normal shock wave, the static properties are functions of
So
yes,
Mach number.
Mach number. Yes, it
Mach
is
number,
a
sir.
function
Option
of
C.
Mach number alone. Okay. Then across the normal shock wave, what will happen? Total temperature remains same. Total temperature increases. Total temperature decreases. Does not depends on temperature. Anyone? Answers from anyone?
Total temperature remains same, sir. Means
Sir,
there is
total
no heat
temperature.
addition now, sir.
What?
Since there is no heat addition, sir, total temperature remains same.
No. No.
So actually option B, sir.
Let's see here. I'll show you the properties. Sorry, here the total temperature, I think it remains. So here the total temperature remains same. It won't change because there is no heat additions and all. So
That only I have told, sir.
yes, correct. You are right only. Only the static temperatures same will be changed. Total temperature won't be changed. Okay. Then shall we solve this problem? The entropy increases across a normal shock wave is 199.5 joule per kilogram Kelvin. Then the ratio.
Sir, I have doubts, sir. Hello?
Yes.
Sir, total temperature remains same. Then the static temperature, sir, that also means
No,
So
no.
actually, static temperature rises now, sir.
Yes.
After
Static
the normal
temperature
shock wave.
rises.
Huh.
Yes.
Okay.
Static temperature rises only. Static temperature always rises because there is a change in pressure. Therefore, a static temperature rises. Okay. Okay. Then just try to solve this problem. So they have given a entropy increase across a normal shock wave is 199.5. We need to find the ratio of stagnation pressure P02 divided by P01 value. Please find this.
0.49.
Yes.
So it's 0.499, sir.
What formula you have applied?
P02 by P01 equal to E raised to.
E raised to the power of like S2 minus S1 by R.
Yes. Okay, fine. So the answer is 0.499, or we can write it as 0.5. Okay. Because 499 we can write as 5. So next problem. The static pressure ratio across a normal shock wave. Static pressure ratio across a normal shock wave. P2 by P1 equal to 1 plus 2 gamma divided by gamma plus 1 into M1 square divided by M1 square minus 1, where M1 is the upstream Mach number. Now for a stationary normal shock, that is for a gamma equal to 1.4 and R equal to 287 joule per kilogram Kelvin. The upstream flow conditions are given by 800 meter per second, and the static temperature 300 Kelvin, and the static pressure 1 atmospheric. The static pressure downstream of the shock. We need to find the static pressure downstream of the shock. Please solve this problem. Easy only, you can solve this problem. It's very easy.
Sir, 6.005.
6.005.
005.
1 second. Everyone
So
got the same
6
answer?
ATM.
6 point?
So 6 ATM.
631. I couldn't get your answers.
6 atmosphere. Yeah.
Yes, correct only. So answer is 6.0 or 6 ATM. Okay. 6 ATM. That is the correct answer. So next thing. Hey, everyone got the same answer? Please reply. Everyone got the same answer?
So solving, sir. 1 second.
Okay.
Yes, sir. 6.
So everyone got it. Okay.
Yeah, yes, sir.
Oh, fine. So next problem. Calculate the ratio of kinetic energy to internal energy at a point in an airflow where the Mach number is 2. So we need to calculate the ratio of kinetic energy to internal energy. Kinetic energy is V square by 2 and internal energy is U. See here, ratio of kinetic energy, that is V square by 2 divided by internal energy, that is U or E. Here we mentioned E, so I am mentioning E. So E, you need to find the value for this ratio if the Mach number is 2. Can you able to solve this? Find the answer. Do you guys need any help from me?
So I'm not able to solve, sir.
Okay, fine. Only thing we need to do is we need to substitute the Mach number. We need to change this value of this ratios values, or we need to apply a formula for these things. Okay.
Sir,
So
0.8.
point
Sir, 8, sir.
0.8.
0.8. No.
8, sir, 8.
No. The Mach number is 2 only now. You're getting wrong, I think so. So I will be just solving, just try to find out. Okay. So V square by 2 divided by, we know the formula for internal energy, that is CV into T. Okay. So that is equal to V square by 2 divided by R divided, that for CV the formula is R divided by gamma minus 1 into T. Okay. So we know A square equal to gamma into R into T. So from that RT equal to, we can substitute here straight away in this equation itself. So therefore that is equal to V square by 2 divided by, here it will come A square divided by gamma into gamma minus 1. Okay. So now you can easily find out, because V square by A square, we can write it as M square. This gamma by gamma minus 1, it will go in the numerator side. Now solve the value and substitute the value and tell me the answer.
1.14.
1.14. 1.1. Everyone got the same answer? So here just, so that is equal to V square into gamma divided by, sorry, gamma into gamma minus 1 divided by 2 into A square. Okay. So V square by A square, we can write it as M square into gamma minus 1 divided by 2. So M square 2. What will come? That is equal to 4 divided by 2 into 1.4 into 0.4. 1.4 into 0.4.
So I'm getting 1.12, sir.
Yes, 1.12. So the answer is the ratio of kinetic energy to internal energy is 1.12. Okay. So now you can able to solve some problems. If I am given any problems in normal shock wave, you can able to solve. Whether you can able to solve this. Students?
A lot of practice is required, sir, to have all these formulae in mind. So we
Yes.
need to practice it.
Yes, in aerodynamics there are so many formulas. So anyhow, you need to mug up or do some things for by hearting all these formulas. If all formulas you know means only you can solve the thing. Okay. Some formulas it is easy only. There is a basic formulas and all. You need to by heart the big formulas for normal shock wave. You need to by heart the formula for finding the downstream Mach number. That is M2 and M2 relating formula we need to by heart. Same way for if you are they have given any values for infinity, we need to by heart the value that is 0.378. This is how likewise some formulas and some values you need to by heart it. Just note down all the values and whatever things I am stressing that just note down this values, note down this formula, just note down that formulas and that values, so it may be helpful for you. Okay, so today's session it is enough. So in our next session we will be seeing that oblique shock, Prandtl-Meyer expansion and expansion problems, expansion wave problems, that is very important, and theta beta relations and remaining things, critical Mach number and drag divergence Mach number. Okay, now it is enough.
So tomorrow's questions till this oblique shock wave, till normal shock waves, sir?
Yes, till normal shock only.
Okay, sir.
Okay. Aishwarya ma'am? Hello, ma'am? Aishwarya ma'am? Yeah, ma'am, I finished for today's session. So I'm winding up, ma'am. Ask students to leave now. Okay, ma'am. Thank you.
Thank you, sir.